In this video, I'm going to analyze the launch of Falcon 9 and Crew Dragon 2 spaceship, and I will be using some of the data from the launch to verify theories relevant to universal gravitation we talked about in Physics 12. So first, let's briefly go over the structure of a Falcon 9 rocket and the different phase during the launch. So this is the Falcon 9 rocket, and it's a two-stage rocket. Below the red line is a first stage rocket. On the bottom of it, there are 9 Merlin engines. Each engine can provide up to 845 kilonewtons of thrust. Together, they can provide up to 1.7 million pounds of thrust force. Very powerful. And above the red line, this part is the second stage rocket. It has 1 Merlin engine that will be powered on after the first stage separation. It can provide about 981 kilonewtons of thrust. On the very top, it is the payload, and what you are looking at right now is the fairing. It's basically a protective cover, and inside there's either satellite, or in this case it's the Crew Dragon 2 spaceship, which doesn't have a Merlin engine, but Crew Dragon 2 spaceship does have 16 Draco thrusters that can help it reorient itself and fine-tune its position. So now let's take a look at the different phase of the launch. So this is the initial launch, and after that the rocket will ascend into the sky. At about 2.5 minutes into the launch, the first stage rocket will separate from the second stage rocket. This process is called MECO, that we'll talk about again when we go over the live video feed. And then the first stage rocket and second stage rocket will go through different paths. So let's follow the first stage rocket first. Shortly after separation, it will go through a process that's called flip maneuver, in which the engine will reorient the rocket to prepare for the entry burn, and eventually the first stage rocket will land on the drone shape, and the second stage rocket will separate from the Crew Dragon 2 spaceship at around 12 minutes. And then after that, the Crew Dragon spaceship is on its own, heading to the International Space Station. So now I'm going to go over the live video feed, but I'll refer back to this chart so that you can identify different phases of the launch on the live video feed and on this chart. Okay, so let's take a look at the video feed. Right now it is the initial launch, very exciting, magnificent, beautiful thing. So this is the initial launch. Unfortunately, shortly after that, the video feed on the rocket is cut off, and it only resumed about 6 minutes into the launch. So let's fast forward to this 6 minutes into the launch. And there we go. So you're actually looking at a couple of things right now on the screen. Let me go over all the things you are looking at here. So first of all, on the right, what you're looking at is the first stage rocket that already separated from the second stage rocket, and now is falling back to the Earth. This is actually the interstage with the fins for stabilization for the landing. It's part of the first stage rocket. And on the left, the screen is showing the Merlin engine of the second stage rocket. So left, second stage, right, the first stage. And here you have the reading of speed, instantaneous speed, and altitude for the second stage rocket. Okay. And on the bottom, this is the important part, you have the timeline. And on the timeline, there are events that are scheduled to happen to the right of the middle line. So this is the middle line. to the right, there are events that are scheduled to happen. Okay? Like this is the entry burn, that's the landing burn, and SECO. I will explain those events later. And on the left, those are the events that have happened. Okay? Like MECO refers to the main engine cutoff, which already happened, but we didn't get to see it on the live broadcast. So right now, this stage or this phase we're looking at on the chart, it's about here, somewhere over here. Okay, after the first stage rocket separated, and this MECO happens around here, and entry burn is gonna happen in a few minutes. So let's now fast forward to the entry burn. Alright, here we go. So right now, if you look at the first stage rocket, on the bottom there's nothing there, right? No fire, nothing. That means the engine is not turned on yet. And this is the timeline. You can see it's about to happen. Once it gets to the middle, this event will happen. So let's see that happen. Right about here. There we go. See the fire coming out of the engine. That means the engine is light up and is ready to slow down the rocket to prepare for the landing. And on the chart, let me show you on the chart, it's over here, right? The entry burn. So and there are two events that are scheduled to happen. Right after entry burn is the SECO, which refers to second stage cutoff, and so this is for the second stage rocket, and then landing burn is for the first stage rocket, right before it lands. We'll come back to those two events later. Right now, I want to show you the most exciting part of this launch. It's the landing of the first stage rocket. It's the recovery of the first stage rocket, which is the best selling point of SpaceX. So let me fast forward to the landing part. Alright, so what we're looking at right now is the dome shape that the rocket will land on. However, we're not able to see how it lands on the dome shape because there's gonna be a expected loss of signal when the rocket is landing on the dome shape, like this, and it's expected because the satellite camera on the dome shape, the signal of it will be disturbed by the impact on landing. So for that a few seconds when the rocket is landing on the dome shape, you won't be able to see it, but shortly after that we're able to see. Now is the exciting part. It's now on the dome shape, right? SpaceX is the first company and private company that is able to recover the first stage rocket, which is the most expensive part of the rocket, and that will greatly lower the cost of space travel. And you may ask, why can't SpaceX do something so that we can actually see it lands on the dome shape? Of course, there are solutions. They can get a second dome shape with a camera on it, so it won't be disturbed by the impact from the landing. However, I think at this point it's not their primary concern, and it's not worth the money to invest on a second dome shape just because of a few seconds of signal loss, right? We can still see it lands on it's on the dome shape right now. Okay, now we're done with the first stage rocket. Let's go back to the second stage rocket and let's talk about SECO. What's happening during SECO? Alright, so before SECO, again refers to second engine cutoff. That's when the engine of the second rocket turns off and prepare for the separation from the spaceship. So before that happens, you can see the Merlin engine is like turned on, light up, very beautiful, like into a fireball. After cycle, you can see the difference. Let me fast forward. Alright, so this is what the engine looks like after cycle. You can see it turns into black because it shuts off. And right now, the rocket and the spaceship is in free falling because there's no power on it anymore, and it can be proven by this really funny little dragon toy brought by the astronaut. You can see it's floating around, right? So which means it's a 0G situation. The spaceship and the rocket right now is in free falling. Alright, and the last thing that's gonna happen is gonna be the deploy, which is the separation of the second stage rocket and the Crew Dragon 2 spaceship. So let's fast forward to that. There we go. See, it's happening now. That's the separation right there. Okay, and on the chart it is here, right? So now we went over the major things during the launch, and next we're gonna do some quantitative analysis using some of the data of the launch. If we go back to around 9 minutes 38 seconds into the launch, you are able to see for the next at least 10 seconds or so, you can see the speed and the altitude both didn't change. How do you explain that? It looks weird, right? The rocket has a speed, but it doesn't change the altitude. The only explanation is that the rocket right now is in a constant circular motion. Okay? I'll also, if you don't understand this, I'll show you with an animation. So this is the Earth, and this is the rocket, and this is the orbit of the rocket. So now let's take a look at a portion of this orbit. Say just this part, and between any 2 points on this orbit, the distance to the center of the Earth, or what we call the orbital radius, are the same. And since the Earth radius are also the same, and orbital radius minus the Earth radius, we get the same altitude. Okay? So that's why the rocket must be in a circular motion for the altitude to not change when it has a really high speed. And it's constant uniform motion, circular motion, sorry, because the speed didn't change either, right? And we can use those data and to actually verify some of the theories we learned in class. So basically the idea is we're gonna take the altitude data, 198 kilometers above the ground, and we're gonna plug it into our universal gravitation equation, and we're gonna calculate the theoretical speed, and we'll compare it with the actual speed on the live video feed and see if our theory works. And right now the rocket is in circular motion, and the universal gravitational force is providing the centripetal force. So we will have this equation, and on the left is the universal gravitation, and on the right it is the centripetal force equation, and they're equal. From there we can arrange the equation and get V by itself, and G is the universal gravitational constant, m is the mass of the Earth, and r is the radius, the orbital radius, which is equal to the Earth radius plus the altitude. That's when the altitude comes in. So basically, we can calculate R by adding the Earth radius with the altitude. And we plug all those numbers in the equation, we can get a speed of 28,042 kilometers per hour. And you can already see it's actually quite close, not far from the actual speed, 27,009 kilometers per hour. And if you calculate percentage error, it's really impressive, 3.82% difference. So with this simple equation, we can get a speed really close to the actual speed. However, there is still room for improvement because in the broadcast, the broadcaster did mention the low and high orbits are respectively 190 kilometers and 205 kilometers, which means the orbit is not a strict circular orbit. It's actually, so it's not a circular orbit, it's actually an elliptical orbit, an ellipse. So if we use the equation for elliptical orbit, we may be able to improve our result. So, and this is the major axis of the ellipse, which is the longest side of the ellipse. And this is the high orbit, and that's the that's a 190 is a low orbit, and 205 is a high orbit, and they are respectively this part and this part on the graph. And this is the equation for velocity equation for elliptical orbit. If you're interested in how we got it, I can comment below. And for now, to save time, I'm just gonna give it to you. And this R is the same as we did in circular motion. It's the orbital radius, and A is the semi-major axis of the ellipse. Which means it's half of the major axis. Then the question comes down to how do we calculate the major axis of the ellipse? In fact, it's quite simple. This is the major axis of the ellipse, right? And you already have the high and the low. You just need to add the diameter of the Earth, which is 2 times the radius of the Earth. So from there, we can calculate the major axis, then divided by 2, we get the value of A. Then we plug everything back into the equation, we get a speed of 28,032 kilometers per hour, which is slightly better. In the circular motion, we got 28,042 kilometers, right? And if you calculate the percentage error, it did improve a little bit, 3.79% instead of 3.82%. However, that also tells us the elliptical orbit is not the major reason that accounts for this percentage error. So what could possibly be accounting for this percentage error, even though it's not small, even though it's not big, but we still want to find out why. I propose 3 reasons. First, it could be due to gravity pull from other celestial objects like the moon or asteroid. And it could also due to atmospheric drag. And the last reason is what I think the most likely one, the thrust force. So if you look at our prediction, like the calculated result from our equation compared to the actual one, it is always greater, and that means there must be a force that's counteracting part of the universal gravitational force. Okay, that's why our theory is a bit bigger than the actual. So what force is counteracting the universal gravitational force? It's going to be the thrust force. And it's going to be more accurately, it's going to be the vertical component of the thrust force. So it's going to be this component that's counteracting the part of the universal gravitational force. And so from there, we can actually calculate the thrust force. And to save some time, I'm not going to go into details about the calculation. It's all on the screen. You can take a look at it if you're interested. But the result we get is we get a thrust force of almost 70,000 newtons. And it is smaller than the maximum of thrust that can be provided by the Merlin engine of the second stage rocket, which means it's totally possible that the engine can provide some thrust to counteract some of the gravitational force to have this uniform circular motion. And by the way, those data, I get those from the SpaceX website. Those are the data sheet. You can take a look at if you're interested. So anyway, I think it's quite impressive that using just a simple equation we learned in Physics 12, we can get a value that's very close to the actual speed. So hopefully you enjoyed the video and check out other videos in the channel.